Hello again. So this time we're trying to model a drying process in Aspen. We're using the same file that we used for the milling process. So that means we're also using the same biomass stream. But aside from the biomass stream, we need to add water, which will represent the moisture liberated from the biomass, oxygen and nitrogen, which will represent the air used for drying. So with that out of the way, we can go into the main flow sheet. So you can see from the previous video, we have the crusher there, biomass stream going in, and the milled biomass going out. So to have a drying process, we'll now add an R stoich from the reactor. So R stoich there. And then we'll also add a flash separator just to the right of the R stoich. So what the R stoich is for is to convert the moisture in the biomass into water using a chemical equation we'll set up in R stoich. And then the water separates from the biomass in principle in the R stoich, but physically it will separate in the flash tank. Right? So we have to set up one stream going into R stoich, which we'll rename as hot air. Hot air. Another stream going from R stoich to flash. One stream at the top of flash and another stream at the bottom. Right? We'll rename that wet air. And we'll rename that dry biomass. Yep, so dry biomass or dry biomass because of the character limit. So we have that. That's our drying setup. But remember that the biomass we put in the crusher is wet and it needs to be dried before it goes into the crusher. So let's just take that, right click, and go to reconnect and select reconnect destination. And connect that to the input of our stoich over here. Right? So that means that instead of going straight into the crusher, it goes to the dryer first. And then the dried biomass should just be reconnected. So again, right click, reconnect, and reconnect destination to the crusher. Right. Right. When that's done, let's just rename B2 as the dryer. And B3 as flash. And then let's rename B1 as the crusher. Right, so after we have all that set up, let's specify all input streams, hot air, and biomass. But remember, we've already specified biomass in the previous video. see, we have specified the proximate analysis, ultimate analysis, and sulfur analysis, particle size distribution also. So there's no need to redo that. Just need to focus on hot air. Right, so for this exercise, we're going to use hot air at 170 degrees Celsius and 1 bar with a flow rate of 200 tons per hour. Tons per hour. Right? And then, as we know, air can be represented by oxygen and nitrogen. So we'll just use mole fraction. Oxygen is 0.21 and nitrogen is 0.79. So hot air is done. Right. The next thing we need to set up, if you look at the simulation window over here, is we need to specify the dryer and the flash. But we'll do the flash first because that's easier. So right click on flash, click input. So for flash, we'll specify adiabatic conditions at atmospheric pressure, so 1 bar and 0 duty. And that represents the process being adiabatic because no heat is lost or exchanged from within the process. And now specifying the dryer, go right click on our stoic input. For the dryer, we do the same. Specifications, duty will be 0 and pressure will be 1 bar. And then for our stoic, of course, we need to specify a reaction. The main reaction occurring in this reactor would be biomass to water. So since biomass is a non-conventional material, the specific components are not really specified. And we can model this liberation of moisture from the biomass through a chemical reaction. So on the Reactions tab, click New. For the reactant, select Biomass. Click and enter -1 for the coefficient. And for the products, select water. And the coefficient is 0.0555084, which represents 1/18 of a mole of biomass. Since the software Aspen uses the molecular mass of 1 gram per mole for biomass, and for water it's 18 grams per mole. Every 1 mole of biomass converts to 0.0555084 moles of water. And then we want to dry the wood from the 52% moisture to 20%. So 50 to 20, that's a difference of 32. So we'll say 0.32 conversion of component biomass. So that means that out of the 100% of biomass, 52% of that is moisture. And out of that 52, we want the 32 to be liberated as water. So that's why we're converting 32% of biomass to water. And that's what the fractional conversion is for. Then if we click next, the reaction updates on the reactions tab. And everything's blue. So that's perfect. So drying the biomass changes the component attributes for moisture in the proximate analysis. And since other elements in these analyses are on a dry basis, drying your biomass doesn't change the attributes. So to account for the moisture loss, we go into component attributes and select substream ID NCPSD. And in component ID, we choose biomass. And in attribute ID, we select proximate analysis. Right, and in the moisture field, we enter the value of 1. So we do this to say that this is changing to that value when the R-stoic block is run. Right, so going back to the main flow sheet, everything looks done, but we have to set up a calculator to control this R-stoic block. So we just go into manipulators, select calculator, then create a calculator at the bottom of dryer. So this calculator, it's not a process block, so we don't really need to connect it to anything. What it does is to grab an input from your process that data, and then return that output. So in setting up the calculator block, same thing, right click, click input. Then in here we have 3 tabs with a red circle: define, calculate, and sequence. We'll start with define, and we'll define 3 variables. First is H2O in, and we'll select for the categories, we'll select streams. Under reference, we choose component attribute var, and under stream, we choose biomass, because this points to the water content that's coming into the dryer, and biomass is the biomass stream coming into our dryer. Substream NCPSD, component biomass, attribute proximate analysis, and element 1. So element 1 points to the moisture content from the proximate analysis. Right. So that's done. We have to make another one, which is H2O dry. H2O dry. So H2O dry is a different one. This time it's a block variable. So under reference, we click block variable, and the block is the dryer block. The variable is component attribute. ID1 is ID1 is NCPSD, ID2 is biomass, and ID3 is proximate analysis, element 1. So it's similar to the first one, but this one is focused on the block rather than the stream. Right. And one more variable, which is conversion, or conv. Conv is another block variable. So we select block var again and use the dryer block and choose the variable conv. And enter 1 in ID1. So this variable conv, it points to the conversion that we specified on the dryer. Right, so with those variables set up, we have 3 there, H2O in, H2O dry, and conv. We can then go into calculate. So in here, we can write Fortran statements that relate these 3 variables. Yep. So here we type H2O dry equals 20.0, which is our target from 52 to 20. And then conv equals bracket H2O in minus H2O dry divided by 100 minus H2O dry. Alright, so this makes sure that our stoic runs until the target conversion is reached. So in this tab, we specify when the calculator block should run, and it should be before the unit operation dryer. So before the dryer block runs, it calculates the conversion. So what it does is, if you can recall from the calculate tab, it assigns H2O dry as 20, and then grabs H2O in from biomass, calculates the needed conversion, and then assigns that to the dryer block before the dryer block runs. So it makes sure that whatever biomass moisture content you enter, it will still dry to 20%. Right. So we specified, if you recall, we specified 0.32 fractional conversion in our stoic. I'll show you here. There. But that's useful because we know that the moisture content is 0.52, and we want to try to dry it to 0.2, which is 20% moisture. But in the case we have to change the moisture content of the biomass for some reason, then the calculator will just adjust that fractional conversion to still have an output of 20% moisture. When that's all done, we can try to run it. So click next. And see the results. Right. So we'll look at the dryer results. We look at the stream summary. So between biomass and dry biomass, we see that the temperature increased from 21 to 114. Mass flow has decreased. So we started at this mass flow 9,000 to 5,000, and the difference is water. See, difference is water, which has gone into the wet air stream. Right. So let's look at some interesting parts. So remember when we did this the first time, the crusher power was 15.6 kilowatts. So now let's look if it's still the same. So with the same size reduction requirements, we now see that the calculated power is 9.369 or 9.4 kilowatts compared to 15 kilowatts when it was wet. So our layout of having the dryer first before the crusher enabled us to use less power to achieve the same size reduction. Right. Then we also want to look at the outlet temperature of wet air. So again, going back to stream summary and looking at wet air, temperature is 114.563 degrees Celsius. So from 170, it reduced to 114 because of the heat imparted into evaporating the water from biomass. So that's a simple and effective way to model your drying process. And that's all for this video. Thanks for listening.